let's kick off. So automated decision making is a key enabler for scaling your business or becoming more significantly more efficient. So when it comes to machines and Internet of Things, they will produce and report on, act on data. So reasoning around data, and as if it would have a temperature scale in terms of hot and cold, it actually does not have a global or formal definition, but it will help us a little bit around reasoning around our designs of an IT solution. So first of all, cold data is typically data that has potential value. You access and analyze it quite seldom, so you don't need frequent access to it, and therefore also latency and retrieving the data is also quite okay. It's acceptable today, but these all lead to that you can actually have quite a cost-effective, cost-efficient design. If you, on the other hand, have a hot data solution where you need instant access always to the data, typically you have real-time data, but it can also be historical data that you actually need very fast access to, then it's typically a hot data solution. So based on these sort of concepts, I will give you 5 key considerations and deep dive into this one at a time on things you should consider when designing your IT solution. So of course, first one is the hardware requirements and hardware cost. You have the second part is compute capacity and scalability. So that's where you add your intelligence, and then how you communicate the connectivity and the different choices you have there, and the latency issues. While you also storage strategies is quite important and will have an impact in your IoT solution. And then of course your ambitions around the future roadmap will also be important. So let's kick off with the first part, hardware requirements and hardware cost. So when you look at intelligence at the edge, it implies that you have an onboard compute in the device that is quite capable to doing intelligence. It can take some decisions on its own, or if it's very intelligent, it can take a lot of decisions. But having intelligence at the edge means you have more compute capacity, more data storage, more sensors, and there's more cooling problems that you need to solve. So there's a lot of design issues here. So normally these devices cost more. And in one sense, that will limit you to possibly only valid for high value use cases. That might not be a drawback, but there's higher investment for higher reward, so to say. But not going this route is not an option to just go for low value cases. The other part is those connectivity technologies that you want to support today, but also in the future. So it's like a time aspect, long product lifetime, lifespan perspective here. Then if you want to be relevant over time, you probably need to make some investment in the device capability and the modem and the different technologies you want to support. And that cost will come up front when you decide on your hardware on the device. But the reward will be that in the future will still be relevant. You don't need to replace it or decommission it. So that's another strategy you can have. But if you remove, or not remove, but if you go to this slim or cheap device hardware, which we call this like the minimum viable product, it's a very incapable device, but it actually gives you the ability to move fast into market. You don't need to have that much money when you start invest. So the devices will itself have quite low cost. But the low cost devices here and the MVP approach actually will probably block you from future revenues. And this is mainly in 2 ways. One is that the technology and the functionality of your competitors and the technology out in the market will shift over time. And the less capable device you have, the less likelihood it will survive and be relevant in the future, where other technologies will dominate. The second part is that when it's very incapable from start and optimized for the first IoT use cases, those other use case number 2, 3, 4, 5, or 6 will probably not fit into this very restricted hardware, where you build more and more advanced IoT use cases. So that in itself will also block you from future revenues because you cannot scale or evolve on that kind of platform. So these are hard balances, but you can have different strategies here. If you move into compute and resource and scalability, I will put this in a context for it, but before I go into the different scenarios. So the primary goal of IoT solutions is automation at scale. And in order to go for or retrieve automation at scale, you typically need to adopt machine learning, because this is key for automation at scale. And if you go for machine learning, you actually need access to data and also scalable compute resources, because these are the two constraints in building good models. And when you train and deploy your models, it actually requires then access to the compute capacity. And here is an old insight that came along with the big data revolution 5-10 years ago, saying that you should co-locate data storage and compute. And the paradigm shift back then was that you usually moved your data to your compute because that's how you did it. You have your data on disk, boot it onto memory or the CPU on your computer, and then process and save it back to disk. But in this case, in the big data scenario back in 5-10 years ago, what you did is you took your compute to where the data was because data wasn't possible to move. So these are some of the paradigms that are actually still relevant also in IoT solutions today. So let's deep dive into those different scenarios. So I will start with scenario A, where we have intelligence in the cloud. So in these cases, the devices report data up to the cloud. The cloud there, you store your data in the cloud, and you have almost infinite storage. You can just add more hard drives. But also you can train your models in the cloud. So there you have extensive capacity to train. You have instant access, only pay for what you need and what you use when you train your models. And then you also deploy your models in the cloud. So as the devices already communicate all the data up and the messages up to the cloud, you can also evaluate the messages in the cloud using the deployed models. And the only thing you need to send back to the device to make it intelligent is the action instructions based on the modeling and the machine learning models in the cloud. Okay, so send data and report back action. What are the nice things with this? Well, it has the scalability feature here. So the scalability compute in cloud is almost infinite. You have no limitations here. So it's for storage. The devices does not need to cost that much. They have very little intelligence. They just report and act. Okay. But you do need to send a lot of data. And whenever you want a decision, you just send the data up to the cloud and then get the action back. That also requires a round trip from the device to the cloud, the modeling evaluation, and then the cloud back to the device. That round trip might be leading to quite high latency. In some use cases, this is not really feasible. But one thing that is important here is that it actually requires stable connectivity, because if you lose the connectivity, so if the device is out of coverage or down in a tunnel or something like that underground, all the intelligence will be lost because that is located in the cloud, so it cannot utilize that. So this scenario A is actually one quite popular scenario, and most use cases actually valid for this, and it's even though it's not the top one we should recommend, it's actually very valid in many use cases. So don't discard this one at all. So if we look at scenario B, where we have intelligence at the edge, so we could sort of go to all the opposite. We have an onboard hardware producing sensors and data, store the data locally. It has a big compute engine and CPU there that it can train locally on the device using all the data that the device has collected. So you train and deploy the machine learning model at the edge. So what does this come with kind of characteristics? Well, the cool thing here is actually it will work offline. It does not need to rely on connectivity because all the data and the knowledge intelligence is localized. This means that you don't need to send that much traffic forth and back to the cloud or backend, and also it will have super low latency. That's very cool. So self-driving cars, etc., should be valid in this use case. Then you have the expensive hardware, because if you need to store a lot of data, have lots of cool sensors and a big compute, that will lead to design considerations that are quite expensive in terms of the hardware. One problem though is that if you need more compute to make the models better, it does not really scale. So if you deploy these devices across the globe, it's rather impossible to visit all the devices and then replace the components on the onboard to get improved compute. It doesn't really scale at all. So you have what you have at start, and that's what you need to live with. With this model, there's one fundamental thing that actually is quite important, and that is, as long as you don't communicate and send all the data somewhere, you only have access to data that the device self-produced. So it cannot learn from other things. So if you would have one device to learn from, or 1 million, I bet that 1 million devices will make you learn much, much faster. But this scenario does not support that. So let's see, we have a scenario C, we will try to address this by sending all the data to all the devices. Well, of course, we can learn from other things, but there's a number of drawbacks where extensive traffic, we have still expensive hardware on board, and it actually now requires stable connectivity to work. And most importantly, again, it does not scale either. Not now so much for that you don't have access to the compute. You have a lot of compute, but all compute is doing the same thing. They're building models locally, okay, with lots of data. So this might work for 100,000, 110 or 10,000 devices, but I bet that when you reach around 100,000 or a million devices, you actually have a lot of bottlenecks now from networking, sending all the data forth and back. You send the data to multiple places, and this just is a factor of it's exponential growth of network load, and so is the data that you need to produce. It's linearly increasing, and there's no way to compensate for that. So this is actually bad practice. So don't think of this as a good scenario at all. But there are probably versions of this out there that are arguably working, but generally this is bad practice. So are there any good balance here between A and B that actually work? Yes, of course there are. We call this the scenario D here, a hybrid solution, where the devices report data up to the cloud, you store data in the cloud, you also train models in the cloud. So all these are like the scenario A up to the left. But then what you do is that rather than having the model deployed in the cloud, you push the model down to the device and have the intelligence at the edge. So that's this small trick you do here. And what happens if you do this? Well, it will work offline. You don't need to report data to the cloud to get the intelligence. You have the data locally and the intelligence locally. So that's fantastic. But you do have the fantastic thing that you actually can learn from other things, because all data, all devices will report to the cloud, so you can learn and build models there. And also, you will have the low latency advantages here, because you don't need to send data to the cloud to have decisions. So that is also nice. And I've actually added here red as extensive traffic, but this is an option here. You can now select how much data you actually need to send to the cloud. Because for decisions, you don't use it. It's just to report data for training and improving the models. So you can do like a filtering and send maybe only a tenth of the data, etc. or something, or only when something important happens, you support, or you send all the data because you want the most optimal way to build the best models. But this now becomes optional how much data you should use over the network. But you do need some expensive hardware, maybe not as expensive as in scenario B, but significantly more expensive than scenario A. That's what I would say. Maybe not super expensive, but there are really good framework from cloud vendors like AWS or TinyML and so on that actually have this scenario hybrid solution, actually a full end-to-end solution for it. So you can look at those. So this is something that I would recommend. It's sort of good practice. It has the good balance of the two scenarios A and B. So okay, timer flies. We have connectivity and latency issues. So there's an ongoing technology shift from 2G, 3G, and 4G into this LTE, Cat-M-ET, NB-IoT, and 5G. These different technologies have different characteristics, where you have 5G and 4G with high bandwidth capacity that, of course, lots of data also drives compute, but it's low latency, which is nice. But it drains battery. And if you would like to have more battery, you typically targeting the LTE Cat-M-ET and NB-IoT, etc., maybe 2G if it's still around. There you have the good battery life, but it comes with quite high latency in terms of sending and communicating the data. So why can't we have both in one technology and use that for everything? Well, this correlation, it cannot be manipulated. And why? Yeah, unless you are a superhero that can violate the laws of physics, because these is characteristics based on physics, okay? So that's just something we need to accept. So we can just play around with these thoughts here and say that, okay, these are the low power use cases that we'll use for they are fit for that. So if we take these and see what do they have, well, they have high latency to the cloud. It's not they are using sleep mode or intelligence between the network and the device, saying that how frequently it should report or say, and so on. So that will in itself introduce high latency. But also the radio bandwidth that we have, or radio waves, also it means that we have quite low bandwidth. In the NB-IoT use case, we actually seen that it sometimes even limits you the ability to update the firmware, because the firmware is so big, even if it's less than a few megabytes, it takes ages to just send that data down to the device. Okay, so that's how low bandwidth you might expect in these scenarios. So what does this mean in terms of decision making in the cloud? Well, it doesn't really fit for centralized decision making. So let's see if we can push the intelligence back to the devices at the edge. And if we do that, we actually will need more compute at the edge. And if we need more, it will consume more compute at the edge, will actually drain the battery. So the primary purpose of these technologies, which is sort of low power here, they will not be very fit for either scenario of automated decision making. Okay. So what are they good for? They are good for non-time critical reporting. And one of these scenarios is like water meters, electricity meters, or gas meters, where you just report consumption centrally and then sum that up into an invoice and send the invoice to the customer. There's no actual decision making done by either the cloud or the backend or the device. It's just a reporting solution, more or less. So that use case, that the last one on meters, actually also fits this cold data use case, where the devices at the bottom here are reporting data. And if you want to store all the data for some reason, you can do it in the cloud or data center using a concept called data lake. There you have hard drives, which are cheap, and in the cloud you can add these almost incrementally all the time or seamlessly, so you can store a lot of data. But the way you store data, it comes with high latency. So it's sort of cold data here, because you don't sort it up front, you don't format it for and querying it then when you need to be very lucky or yeah, it's not fast to retrieve or store data here. So that means if you're going to do logic on any data from the data lake, it will be rather old, meaning that if you're going to automate something, it will act on old data, meaning that it probably takes wrong decision. So data lakes are not to be used for automation, but it will work for batch reporting, and it will work for building data sets for training your machine learning. But the problem here is that if you do that, there is no way in this solution to deploy your machine learning model for automated decision making. You can do it for like finding patterns and learning stuff, but artificial intelligence and replacing humans in decision making here in a very fast and scalable machine like scenario, it doesn't really fly because of the latency is too high. It's too late to make the decision. That's normally what. So data lakes are not for automation, but you can warm the data up, so to say. You can replace the data lake with a database. This is all still using disks storage, but you have a software on top that makes it rather fast. So this actually may allow you for automation of your business logic, which the data lake wouldn't. However, there is one caveat. So when you scale your device fleet into like 100,000 millions or many, many millions, what will happen is that they all report data to the cloud, and they try to write to the same database now. If it's a relational database, it might actually cause either queues or even loss of data because the database is busy writing data from someone else when you report it from your device. So that might be congestion, meaning that the data, when you analyze it and you automate your business logic or asking questions or automating based on the data in the database, the data will actually be old. So you have the same situation in the data lake. So this works for not too big deployments. And there are databases that support high read and high write, but the traditional or relational databases will likely not. So be careful there. But for intermediate sized use cases, this is a perfectly valid and quite normal way to do it. However, if you have the hot data case, so in case you have, for instance, like a building where you have connected doors that you are measured if they're open or closed, you have windows that you know if they're open or closed, you have ventilation with airflow measures and sensors, you have temperature, air quality, stuff like that. You have indoor doors that you know are open or closed, so you can measure everything about the air quality and airflow. And if you want to compensate if someone leaves a window open or a door is open during winter time, and it will just flow a lot of cold air into the building, you want to automate your climate system. So if you're going to do that, it sort of requires almost real-time data, depending on how fast you actually will change. But the scenario here might be that if it takes a little long time to write to the database and read, it will actually be that when you open the door and it will take you several minutes to get that insight, it's already closed when you get information to say, okay, high temperature because winter air is coming in. So then it will have a really bad scenario. You act on the wrong information, and it's then trying to overcompensate. It's called in something in Swedish, which I don't know. Yeah, it doesn't go well. It just goes worse and worse. So there's a solution to fix this. One, and that is actually to store the current state in memory. So memory storage is quite expensive. But if you only store the current state of all the different sensor values, you will have the low latency here. You can still store the historical data for seasonal patterns and so on in the database. So this kind of strategy with the storage and hot and cold or in warm will actually serve many purposes at the same time and strikes a good balance of cost and efficiency. Okay, so last out is the future roadmap ambitions. So here is typically, time to market versus how long product lifespan are you expecting. And you can think of it like this: are you able to predict the future? Well, then you can actually plan optimally. You can decide exactly what kind of hardware you need, what IoT solution you need, what sensors, everything. But you don't normally know and are very good at predicting future. You may or may not. The other strategy you can have is that you will win by being first. So reaching the market, time to market is more important. And you don't plan to stay on the market very long. You think that you will not be the best, but as long as you're first, there are revenues to reap. Okay. So when other competitors are launching their product, maybe then you'll give up and do something completely different. That's another strategy. Time to market is everything. Then there's a sort of this other strategy that where you acquire strategy, the strategy is that you want to evolve and adapt along the road. So then it's a matter of like not closing doors. So that might be actually a strategy for those that have a lot of uncertainty. And you can also differentiate your use case towards maybe competitors to still be relevant on the market, or improve them and beat them by evolving. So that is all. here are my conclusions and recommendations in summary. There is a guideline PDF document and webpage now online on the telenorconnection.com webpage. You can scan the QR code or just follow the link below. But in essence, using data as an asset when designing your IT solution actually can help you. You need to have some trade-offs in mind. You need to think about the cost, where to locate your compute intense workloads, the complexity around how complex the hardware should be, and whether time to market or lifespan of your product is relevant. So one way to approach this is to assess if your use case and your need of data, is it hot or cold? That will also help you in designing your IT solution. So if you need instant access, okay, then it's hot. What does that mean for your design and your connectivity and your backend or edge versus cloud intelligence, etc. So one more thing then is that be very conscious that your future use cases might have significantly different demand on data than your first and second use case. And if there would be one advice going forward, I would say that strive for an IoT architecture that enables evolution into new IoT use cases without need to replace the key components in your solution. And the device might be one of them. Maybe your buildup of data will be another, etc. So don't set for an architecture where you cannot evolve on and where you need to replace everything, because beyond that you cannot, at a certain point you cannot evolve any longer. Okay, so thank you very much and have a great rest of the day.